In this section, we will discuss Donsker invariance principle, which will be convergence in distribution of a random walk properly rescaled to a Brownian motion, in the space of continuous functions on 0 infinity. So in the last section, we defined Brownian motion, so this process xt indexed by t on 0 infinity. And it was a continuous process, so we can view x as taking values as a function of t in the space of continuous functions on the half line, positive half line. Now, the space of continuous functions can be endowed with a metric, and we'll choose the metric d to be a metric that metrizes uniform convergence on compacts. So, where d between two functions f and g is given by this usual construction, where dn is just a sup norm on the interval 0n. So this metric, you can see that the distance between some sequence fj goes to 0 and a function f goes to 0 if and only if dn goes to 0, right, for when j goes to infinity, here for all n. So on each compact you have this uniform convergence. For the same reason, because of this equivalence, we also get that this space of continuous functions that we are looking at with this metric, it's both separable and complete. Because we know that continuous functions on a compact with the sup norm is complete and separable. So a Brownian motion is a random element in this very nice metric space, which is complete and separable, and we want to prove the convergence of some other stochastic process to this in distribution. And so let's recall that when we discussed convergence of probabilities on metric spaces, especially such nice spaces as separable and complete, we had the following type of criterion. If we have a sequence of probability measures converging to some probability measure p on a complete separable metric space, but let's just focus on the one we have at hand here, then to check this, you can check the following two conditions. So first of all, a necessary condition is that Pn is uniformly tight. So if you remember, uniform tightness plays a key role in the study of convergence of probability measures on metric spaces. Which means that, in other words, for every epsilon, you can find some compact k in this space of continuous functions, such that the probability En of the complement will be smaller than epsilon. And this should be true, so uniformly tight means that this is true for all n. So you find one compact that works for all measures in this sequence. And number two, that finite dimensional distributions converge. So in other words, when you take your continuous function and look at it at finitely many times t1, tn, the distribution of those random variables should converge on Rn. And the reason why 1 and 2 imply convergence, if we recall that the first condition ensures subsequential convergence, right? That sort of uniform tightness means your probability measures do not run away to infinity. So for any sequence, you can choose a converging subsequence by selection theorem. And convergence of finite dimensional distributions ensures that all your subsequential limits are the same. Right, and that's by a lemma that we discussed in the previous section, that the Borel sigma algebra on the space of continuous functions, it's just a cylindrical sigma algebra on the space of all functions intersected with this space of continuous functions, right? And cylindrical sigma algebra is generated by cylindrical algebra, and probabilities of cylindrical events are exactly our finite dimensional distributions. So when we want to prove convergence of some continuous process to a Brownian motion, we have to check that finite dimensional distributions converge, and that will be something that will follow directly from the central limit theorem in this particular result that we are going to discuss. And so the main work will be to show uniform tightness of the sequence. Okay, and in particular, this means that we have to consider some characterization of what it means to be a compact on this space of continuous functions. And luckily, this is given by Arcelà-Ascoli theorem. So let's recall the Arcelà-Ascoli theorem. First of all, it's a statement about equicontinuity, so we'll give some definition here. Namely, given any t bigger than 0, and given any continuous functions which we will denote x, so x will be elements of the space of continuous functions, we'll denote the modulus of continuity of x on this interval 0t by mtx delta, right? So for positive delta, this is just a supremum of the increment of your function, so xa minus x of b for all choices of a and b in this interval 0t within distance delta from each other. So a minus b is less than or equal than delta. So this is a modulus of continuity of x. And then Arcelà-Ascoli theorem tells us the following. It says that K is a compact in the space of continuous functions on the positive half line with this metric that metrises uniform converges on compacts. Okay, if and only if you have uniform boundedness. Now here we have to check that our set of functions is just bounded uniformly at one point, at 0. So supremum over all functions in this set evaluated at 0 is finite. And then the equicontinuity means that as this parameter delta goes to 0, uniformly, so supremum over all functions in this set of the modulus of continuity goes to 0. Okay, and since this metric D metrises converges on compacts, we have to check this for every compact. So in other words, we have to check this for all, let's say, positive t, or you can restrict to for all integer t. And so in this two conditions, right, the first, well, together with the second, basically ensures that our set is uniformly bounded, right? And the second condition is that it's equicontinuous. Okay, and once we have this characterization of compacts on our space, we can now translate this to re-express more explicitly what it means for a sequence of probability measures to be uniformly tight. Okay, and that will be given by the next theorem, okay, which says the following. The sequence of probability measures Pn on the space of continuous functions with the above metric is uniformly tight, okay, if and only if the following two conditions hold. So the limit when lambda goes to plus infinity uniformly over all n, that the probability Pn of the event that our function at 0 exceeds level lambda is 0. And the second one is that the limit when delta goes to 0 from above, again uniformly over n, of the probability that this modulus of continuity on the interval 0t of our function x with parameter delta exceeds epsilon is also 0, and this holds for all t and all epsilon bigger than 0. Okay, this is just translation to the probabilistic language of the uniform boundedness and equicontinuity condition above. Okay, and the proof of this is completely straightforward. So in one direction, if we take some parameter gamma, okay, and then if we can find a compact k in our space of continuous functions, okay, such that the probabilities Pn of the complement are less than or equal than gamma for all n. In other words, we are using a uniform tightness, right? Then by Arzelà-Ascoli, we know that the supremum over all functions in this compact evaluated at 0 is bounded by some constant lambda. So in particular, for this lambda, the first condition holds, right? That the probability that x at 0 is bigger than lambda, this implies that x is not in this compact. So this is bounded by the probability that x is in the complement, and this probability is less than gamma for all n. And similarly, by Arzelà-Ascoli, because of equicontinuity, right, for any epsilon, we can choose this parameter delta such that uniformly over all functions in this compact, the modulus of continuity of x at delta will be less than or equal than epsilon. Okay, this is for a fixed t. And again, the second probability in the statement of the theorem, namely that this modulus of continuity exceeds epsilon, means that our function x is not in this compact. And so this is bounded by gamma. Now, in the other direction, one has to work just a little bit more. And so let's fix some positive gamma here. And then on each finite interval from 0 to t, now here we will want to look only at countably many. So we'll take only integer t. So let's take integer t, and also let's consider integer k. Now let's find first the parameter lambda t such that the probability that x evaluated at 0 exceeds this lambda t is less than gamma over 2 to the t plus 1. So for any gamma, by the first statement, we can find such a lambda because this probability uniformly goes to 0. Right? And the second statement allows us to find, so let's find this parameter delta here for any t and k, again such that the modulus of continuity, now the probability Pn in both cases. So Pn, that the modulus of continuity on 0t of x evaluated at delta tk. Now here I'll take greater than 1 over k. So for this particular choice of inequality, that this is less than or equal than gamma over 2t plus k plus 1. Again, when delta goes to 0, this probability goes to 0, so we can choose such a delta for any choice of gamma. Okay? And in particular, now let's consider a set of functions on the complement of these two conditions. So let's consider the set AT to be all continuous functions such that x of 0 is less than or equal than lambda t, and that modulus of continuity on 0t evaluated at this delta is less than or equal than 1 over k, okay, and for all k. This is for a fixed compact 0t. Let's consider this set. Then we can see that just by the union bound, that the probability Pn of the complement of this set means that one of the conditions is violated, and that leads exactly to the probabilities above. So all those probabilities are bounded by gamma over 2 to the t plus 1, that x naught exceeds lambda t, and all the other probabilities are bounded by gamma over 2 to the t plus k plus 1. Okay, and so this is gamma over 2 to the t. And then finally we just take intersection of all these AT. So let k be the intersection over all integer t of this set AT. And again, the probability of the complement, right, it just means that we are in the complement of one of these sets AT. So by union bound, this is bounded by sum over t, gamma over 2 to the t, and so we get gamma. And again, this probability is Pn for every probability measure P. And we just have to notice that K is a compact because by construction it's closed. So this K here is closed, and it's uniformly bounded and equicontinuous on each interval 0t. Okay, for integer t. That's just by the definition of the set A, right? The set A ensures that the modulus of continuity is getting small as delta is getting small above, and here we just intersect over all t, so we ensure this for every interval 0t. So in particular, we get that K is a compact in our space of continuous functions. Okay, so that proves that in this direction that Pn is uniformly tight. Now, one useful remark will be that the second condition in the statement of the theorem, it can be relaxed, and this is convenient when we actually use this theorem. So the remark here is that we can relax the second statement in the above theorem, that the limit when delta goes to 0 uniformly over n of the probability that modulus of continuity exceeds any epsilon is 0, right, we can relax this to the following condition. The limit when delta goes to 0, instead of the sup, here we can replace it by upper limit. So lim sup when n goes to infinity of the same probability is equal to 0. So we can replace this condition star by this relax condition 2 star. And to see that indeed this relaxed condition is actually the same, given this 2 star, right, it just means that for any gamma, the fact that this limit goes to 0 means you can find some delta naught first of all, and then the fact that lim sup goes to 0 means that you can also find some n naught, okay, such that for all n after that, your probability that this modulus of continuity exceeds epsilon for delta naught will be less than gamma. Then for other n, so you have control for n big enough, but for n smaller than n naught, you just use continuity of your process. So for n less than or equal than the naught, let's just use that the modulus of continuity, since we are on the space of continuous functions, all right, this goes to 0 as delta goes to 0 for every x. Right? So for all continuous functions on our space. So by continuity of probability measure for a fixed n, right, the probability that this modulus of continuity will exceed some epsilon will eventually get as small as you like. So you can find this delta n here, so that this probability is also less than gamma, right? So for some delta n. Okay, and then it just remains to take delta, let's say tilde, to be the minimum of all these deltas. So minimum of delta naught that controls the sequence for large n, and then delta 1 up to delta n, these individual deltas that control modulus of continuity for small n. Okay. And the fact that modulus of continuity is monotone, so if you decrease delta, you just improve your statement, means that you have now with this delta the same inequality for the modulus of continuity. Now it holds for all n. So this relaxation, so if we go back to this statement, the fact that we replace the supremum by the upper limit, it's a very basic observation, right? That if lim sup allows us to control essentially all large n, and for smaller n we can control just by continuity of measure. And so when we actually apply the above theorem, when we want to prove uniform tightness, we will use it in the second form. All right, and so now we discuss the basic observations, what it means to be a compact and what it means to be uniformly tight on this particular space of continuous functions. We are now ready to discuss this Donsker invariance theorem for convergence of a random walk, rescaled random walk, to a Brownian motion.